Join us and get to know all about the power semiconductor solutions for 1500 volt solar central inverters. Let's start with some quick notes on the business model of energy generation. Energy generation can be classified as centralized and/or decentralized. Decentralized energy generation produces energy close to the load center. In a residential application, for instance, solar energy is generated right above the roof of the resident. The energy produced in this case is lower than 5 megawatt. Besides residential applications, commercial applications are also another typical example of decentralized power generation. On the other hand, when the energy generation is centralized, it is produced by a few bigger power plants, distant from the demand center and is higher than 5 megawatt. Since this type of energy generation requires bigger power plants and space is a big constraint in cities, the obvious choice is to put them in a remote location. This, by consequence, requires bigger transmission and distribution infrastructures. This type of system is connected to transmission electrical networks, which allows increasing the system's AC voltage beyond the distribution grid's voltage level of 400 volt. The value of the increased system voltage further enables the system costs reduction. A typical example for centralized energy generation is utility scale. The key drivers for the solar inverter's design are system costs and end-to-end efficiency optimization. One of the major trends in utility scale PV solar projects is the change from 1000 to 1500 volt systems. Basically, the value of increased system voltages translates into infrastructure savings, reduced installation costs, and end-to-end efficiency improvements. As time goes by, it is expected that the 1500 volt PV's voltage will be the mainstream for utility scale installations. In fact, 1500 volt PV inverters are expected to account for more than 70% of the three-phased PV inverters shipments in 2023. Moving on to central inverter design specifications, for the 1500 volt PV array, a two-level or neutral point clamp 2 NPC2 topologies using 1700 volt IGBTs are the preferred choice for a 2 to 4 kHz switching frequency operation. The three-level NPC1 topology is widely used due to its low cosmic ray-induced failure rate, in spite of increased complexity during reactive power mode operation and increased system cost. As explained, system cost and end-to-end efficiency optimization are the key challenges for central inverters. To achieve a more efficient and simplified inverter design, the simple two-level or NPC2 topology is now preferred. To facilitate these topologies, industry demands power semiconductors with low cosmic ray-induced failure rate, while maintaining conversion losses as low as possible. Infineon developed two IGBT technologies to meet the market needs. The 1200 volt IGBT7 in dual configuration to build the NPC1 topology, which aimed to decrease the system costs and allow a performance optimization with minimal design changes, keeping the state-of-the-art power level of 1.1 MVA. And the 2300 volt IGBT7 in a simple two-level topology or an NPC2 topology in combination with a 1200 volt common collector configuration, which aimed to address the next level of power and performance but with a change in the inverter's topology. It is common to build NPC1 topology products using 3 standard DUAL PrimePack 3 modules with IGBT4 technology. The next step towards cost and performance optimization in the existing inverter design is possible by switching to an EconoDUAL 3 package. Introducing IGBT7 chip technology in an EconoDUAL 3 with a 2-module parallel configuration enables the designer to reach 8% higher output power at a 3.3 kHz switching frequency operation with almost 10% lower losses. This further improves the inverter's efficiency by 0.2%, which is very impressive. In addition, IGBT7 chip technology comes with a short time overload operation that reaches up to 175 degrees in order to cope with short-term overcurrent operations which occur during grid ride-through events. This enables the possibility to increase the junction's operating temperature as close as possible to its allowed maximum. This may allow the increase of the inverter's power since it will be operated with lower safety margin limits under nominal operation. In fact, it is possible to reach a target power of 1.1 MVA in a 2-module parallel configuration. FF900R12ME7B11 is the best choice for the inverter's design if you are targeting system cost decrease and performance optimization while keeping the same power level. To address NPC2 topologies for the 1500 volt PV applications, Infineon has developed 2 modules. One with a 2300 volt IGBT7 chip in a dual configuration and another with a 1200 volt IGBT7 chip in a common collector configuration. This gives you the flexibility to build an inverter with a 2 or 3 module configuration. But please be aware that the highest power level can only be achieved in a 3-module configuration. This configuration requires 2 2300 volt IGBT modules and 1 1200 volt common collector module. Nowadays, the NPC1 topology is built with 3 PrimePack 3 modules. So, for a fair comparison between NPC1 and NPC2 topologies, a 3-module solution is considered. An NPC2 topology enables the designer to reach a 38% higher output power at a 4 kHz switching frequency operation with almost 1% lower losses. This further improves the inverter's efficiency by 0.4%, which is very impressive. As mentioned, IGBT7 chip technology allows up to 175 degrees, enabling the increase of the inverter's power, which can be operated within lower safety margin limits. Furthermore, it is possible to reach a target power of 1.8 MVA in a 3-module configuration and of 1.3 MVA in a 2-module configuration. So, FF1800R23IE7 and FF2400RB12IE7 are the best choices for the inverter's design when trying to achieve the next level of power density and performance optimization. If you are having difficulties in choosing different semiconductors for your solar power systems, Infineon has a broad portfolio that answers all your needs and fulfills the latest market requirements, from a few kilowatt to several megawatt power levels. Every inverter needs a switch, all switches need a driver, and all drivers need to be controlled. That's why we offer the right ICE driver gate driver and XMC microcontrollers. Finally, each functional block needs an auxiliary power supply. For that purpose, we offer 1.7 kV Cool SiC MOSFET. Hopefully this video was interesting and provided you some hints on power semiconductor solutions for solar central inverters. If you need additional information, just have a look at our application page at Infineon.com. And don't forget to subscribe to Infineon's newsletter for engineers.